All right, so we're going to pick up from where we left off. I'll remind you that we're thinking about this in terms of theta now. That was the last place we left in our last video. Not that that matters too much, because during this part of the proof, they just drop the arguments, which makes perfect sense because it's already quite a mess. But we talked about making these substitutions, right? These substitutions are easy to make from what we've done in this up to this section here, which we talked about in depth, and this section here we talked about in depth. So this substitution is where we're going to start today. No backtracking this time. Now, I will remind you the caveat about the non-standard use of the symmetrization here, so keep that in mind. And then also don't forget, it's really kind of weird because I'm telling you to, remember there's non-standard use of this symmetrization, but I'm also telling you that I have a back pocket secret which tells me this whole term is zero anyway, right? So be aware that the term that doesn't exist is also non-standard, I guess is sort of the weird way I'm saying it. But I want to proceed with it in there, right? Like I said, it's not wrong. And I have yet to prove to you that this is zero, right? It's just me talking right now. The proof certainly works both ways, and it'll be interesting to see why. But we're going to proceed exactly as they presented it right here. So what's the next step that they do? Well, the next step is sort of the obvious thing. You're going to multiply. This is there's two terms here, two terms here, two terms here. So there should be a total of, when you multiply this all out, 8 terms. They only have 1, 2, 3, 4 terms, and that's because they only keep things up to 4th order in lambda. They let the fifth and sixth order terms drop. So this term times this term goes away, and this term times that term goes away, and this term times that term goes away. So what you have is you have the 2nd order terms and the 4th order terms stay. So it doesn't take much to do that multiplication. For example, this first term here is just lambda partial a partial theta I times lambda partial b partial theta I times GAB. And there it is. Then the first 4th order term, that's interesting, is I guess this DCEC term, they put it here, is this term here times lambda b VB, Vj, which is this term here. And so you end up with that term, right? So this getting from here to this line is really easy. You multiply everything out, only keep things up to 4th order. Then they combine everything, which is just garbage collection. And this combination is all just a matter of pulling everything out in terms of lambda to the 4th. So they go with lambda to the 4th over 2, which leaves behind a 3 here, and a, seems like there should be another 3. Hold on. Oh, no. There's not, they combine this term with that term, right? It's the same thing. It's V. They just rename the dummy variables, right? These are all dummy variables, so the F can be changed. The F, for example, can be changed to, let me blow it up. This F and that F could be changed to the letter D, which would match that. Then this G and that G could be changed to the letter E, and then that would match. And the H could change to H, and then that would match with the C and the, where's the C? Here's the C. So these dummy variables can change. So this term here, so this term here and this term here can be combined into just one term, right? So that's why you only get, so that's why you can pull lambda of 2 out of that. Wait a minute. No, it's the wrong term, right? Those 2 terms can be combined in this term, right? And the combination isn't perfect. You're left with this sum. Actually, you know what? We should be a little bit more careful, because it's worth really seeing how this builds up. So let me blow this up. And what we're gonna talk about are, all right, these, we know that the dummy variables can be arbitrarily changed in name. So I could change the name of G, for example, without any problem. Same with B. I could change the name of B without any problem. And so we could, there's a lot of dummy variables between this term and this term that we can make the same. But there are some variables here there's some indices that are not dummy indices. For example, the I on the theta, That's not a dummy indice. That's established over here. That's left behind. There's no pairing of I with any other, there's no summation of I. So I and j, those guys are fixed. And likewise, it's the same I and j over here. So if I equals 1 here, I equals 1 there, right? I equals 1 on every term. So the I and the j cannot be adjusted. So if we look at this term here, what we see is that I'm going to put a slash through everything that we can just immediately change with the other term, right? For example, I can immediately take this f and this d, and they're the same. I can take this g and this e, and I can make them to be the same. I can take this h, no, not the h. I can't do the h. In fact, I better clean up what I have. Okay, there's a little tighter. Now, what about this a? Well, that a contracts over this a here in the metric. This a in the metric contracts over that a there, right? So these a's really don't refer to the same thing. Even though they're named the same, they don't contract the same way. So renaming a's doesn't actually help me. What about b? Well, here b contracts over this partial b, partial j. And here this b contracts over that b, and this a contracts over partial v, partial I, right? So I can't just rename the a's and the i's. Now also this h, the a's and the b's. The h is a problem too, because here the h contracts over partial v, partial theta j, but here the c goes partial b, partial c, v, partial theta I. So I can't just adjust that either. So I can make a bunch of adjustments, but not everything. And the things that are left behind, I have to kind of literally leave behind. So I make all the changes I can, and then I create this sum, which accounts for the fact that these partials here, this partial derivative and that partial derivative, right, which would be the same as these two, right, they contract differently. So I create a sum that pulls those two guys out, and this piece, right, is going to mimic the partial with respect to I going into the last indice on the connection. So the partial index with respect to I, whoops, that would be over partial index with respect to I going on the last indices in the connection. So this term gets mimicked by this, and this term finally gets mimicked by this guy with that. So I combine them, but I can't completely combine them, right? I have to be very careful that this, after all the dummy indices are accounted for, is exactly equal to this with the right partial theta sub I, superscript I, and partial theta superscript j, that the pieces that those two are contracted into are the same on this term, and likewise this guy's its final contractions mimic this. So you can't just add these two together. You can put them together, factor out this piece by playing with the indices that are in fact identical dummy indices, but you end up leaving behind this guy. Now, okay, but so that explains the combination of these terms from this line to this line. The problem is going from this line to this line. What they want to do is they want to introduce this anti-commutator notation. And they define the anti-commutator notation way down here. They say, okay, and this is very standard notation. Sometimes there's a 1/2 out here, depending on some things, but that's not a big deal, right? This is their definition of this bracket notation. You have an object A and an object B, and you multiply them in this order, and presumably they don't commute. Because if they did commute, you would just have 2AB, right? Which is why you might have a 1/2 involved in this. But if they don't commute, you end up with this expression. So they kind of want to use this notation. But here, note very carefully, A is the identical object is put here and here, and B, that object is put here and here, right? Unfortunately, they want to apply that right here. They want to apply that going from this position to this position. And if you look at it, this structure is incorrect, right? This structure here does not mimic that structure here. Because if I unpack this according to the definition, what would I get? If I literally did this, I would end up with that expression right there, right? That would be the literal replacement of this using their own definition, right? I'm using this definition right down here, AB and BA. But if you look, right, I mean, this is absurd, right? This is just a real function. That's a real function. These two commute, right? So I get that. I'm in that situation where I have 2AB, right? These are two commuting functions, right? So this is not really right. The substitution's wrong. And if you look, well, the reason it's wrong is if you look at this, this is not the same, right? This sum is not that. I have partial V, partial I on the left and partial VE, partial theta J on the right, right? This is VE, VI, VE, VI in both cases because, as I said, AB plus BA, A and A are identical. Well, that's identical with that. But this is not identical with this, nor is that identical with that. It's not the same thing. It just isn't the way they defined it. So if you're going through this paper and you're trying to handle this proof yourself, be very careful with that idea. Now, there is some good news, right, about this, which is that it still works. Well, I shouldn't say it still works. It doesn't. It works if you redefine, if you forget this definition, and just define this to literally mean that, right? If this bracketed thing with a comma in it literally means this, you're okay. The reason you're okay, though, isn't because, I mean, a literal change, obviously you're okay if you literally change the definition of that bracket thing. The issue is over here, right? It's over on this side of things, right? Because what happens next is after they make the substitution here, right? After they go from this part to this part, you'll see that they introduce this bracket and then they introduce the bracket here and then they factor the bracket out. So somehow the bracket appears here. And now the problem is geez, with this definition of the bracket being wrong, are they allowed to go from here to here the way they did? Is that legal? Because they've defined it wrong. So maybe you can't make this factorization, right? We've got to check. And fortuitously, despite the error in the definition of this anti-commutator, if you use this new definition, this literal definition, the literal definition, you're still okay. And the reason is because partial V, partial I, and partial V, partial J are being blended into E and B, right? They're blended into the index E and the index B are going to E and B, but G is a symmetric object, right? So this is symmetric, so it effectively symmetrizes this whole expression with respect to E and B. That whole term is symmetrized with respect to E and B. Ergo, if I literally make the replacement based on the new definition for this, what do I get? I'll show you. Okay, so the first step is you get this. That would be substituted right there, right? Well, I guess including the 1/2, because that 1/2 appears as well. So we're going to make the substitution, this expression right here. I keep saying here, but I'm not pointing, right? Here, that expression is our new redefinition of what this thing is, goes right there. Well, now we're going to sum over all of this stuff. CD, let's ignore that for now, right? Because that's just dummied out with the partials. But this GEB thing, so let's incorporate that. So imagine we just had any symmetric object here. In this case, it's the metric, or even the second partial of the metric. But E and B, it's always going to be symmetric over EB. So if you look at this expression summed over E and B, I now have dummy indices, right? This is now the classic dummy Ndc formula. I just take this term here and I change the dummy indices to, well, I guess I split it up. So I have that, and then this is going to be multiplied by GEB. And then I exchange the dummy indices, right? And I change the B to an E and the E to a B, and now I do have this same term twice. So I end up, and then this I just change back to BE wait a minute, I dummied them up and I switched the dummies, but then I changed just this part back to EB, right? Because that's symmetric in and of itself, and I end up with 2GEB times partial VE partial theta I times partial VB partial theta J, right? So because of the symmetrization, and then this is literally, so that I get rid of the factor of 2 by multiplying by a 1/2. So even under this weird definition, it turns out this is fine. Under this definition or under this our weird definition, because we're saved by the symmetrization under the metric. So the point I'm trying to make is, even though we change the definition here, we can still make this transition from here to here okay. And that's all because of the way the metric works. So that's good news. So then once we get to this point, we end up with, right here, and then we just factor out this weirdly defined thing here, and we're left with this last line. And the last line is, just to keep track of what we're doing, it's G tilde ij as a function of theta, right? As a function of theta. This is the metric on Sn minus 1, which is what we've been after, right? This is what we've been after up here, right? Is this thing, and now we've got it. And how do we know we have it? Well, we know we have it because, remember, each of these V's, they're all functions of theta. They're all functions of theta. So you can take these derivatives with theta without any trouble, right? So I don't need to go through the V's anymore. These terms here are all evaluated, this is all evaluated at P, right? So all that's all evaluated. This metric too, this GAB, this metric, that's all evaluated at P, right? Everything that we need to introduce into this problem is either a function of theta or it's evaluated at P. So we've now got an expression for the metric on Sn minus 1 dependent only on our knowledge of the metric at P, which is not even in Sn minus 1, and that's it. It's and theta, right? And P and theta. So this is sort of an answer that we've been after. So that is actually pretty nice, and it's all kind of broken down into this. So, but notice the Riemann tensor isn't anywhere to be seen. But the only place the Riemann tensor could surface is somewhere in here, and that's indeed the next step, right? The next step in the proof is to take this part right here, pull it out, and end up introducing finally something that involves the Riemann tensor. So the next part of the proof goes from here, goes from this thing to this thing. And it isn't easy. It actually depends a bit on this too, right? It depends on understanding this as well. So when they write this equals this, it's a bit of a misnomer. This only equals this, it turns out, because of certain symmetrizations that occur from this. So that's an important thing then. We're going to piece that apart soon. All right, so we're going to figure out how we go from this to this, and I'm going to start by kind of working on this a little bit. The first thing I'm going to do is I'm going to get rid of these partial derivative expressions in the notation. So I'm going to make the purely notational move from here to here. So the partial derivative with respect to d happens first, so it ends up on the right of my slash, and the partial derivative with respect to x superscript c ends up over here. And this slash, where g is going to be symmetric in the two indices on the left of the slash and the two indices on the right, but not obviously symmetric across the slash. And here I do the same thing. I move this c over to here, and then I symmetrize with a slash in there, right? But it's still symmetric, right? It's still totally symmetric. I can shift these around. In fact, I'm going to in a minute. I can shift these around all I want across the slash. Here I can't, but here I can. And then the b comes down because I'm converting from the Christoffel symbol, let's see if I get this right, the Christoffel symbol of the second kind to the Christoffel symbol of the first kind. And by definition, the a will drop here. Notice that there's no slot here. There's no little slot here, right? It's not written T-A-D-E with an obvious space for the a to drop into. I like to put the space in there, but they don't in this case. So, but we know that the convention is almost always to drop it right into the slot. I have seen the convention that goes like this: A, B, C goes to B, C, A. I have seen that convention before. I think in these lectures I've used references that have used that convention before. But that's not the convention we're using here. The convention is that it will just drop, and there it is right here like this. So I've converted this, and I've gotten rid of those partial derivatives. And I've only done that because doing all of the work that gets us to this side, it's just easier to not have to draw all these partials all the time. So I'm just going to do it this way. So that was my first sort of non-substantive, but I think time-saving or trouble-saving step, or confusion-saving step. How about that? All right, so the next thing I'm going to do is I'm going to go to the paper, and I'm going to pull out the context for which this was, this is what we're trying to simplify, right? And this is the whole term that it was a part of. So I'm going to kind of look at these terms for a moment. All right, so my first step here is I'm going to take D, E, and C, and I'm going to permute them to C, D, and E. Now remember, this is completely symmetrized by definition in here. So I can permute those all day long, and I'm still fine. So what the reason is I want the B and the E to be on the extremities of this thing, and because that's going to sort of make it a little bit easier as we go on. It's easier to say, oh, it's the first and the last index I'm interested in. So it's a small change, but it's a legal change, though. Once you've symmetrized something, you can exploit that symmetry however you wish. So now, looking back at the context of where this all fit in, we see that this expression was multiplied by this stuff over here. So let's actually consider that actual multiplication, right? So the way I want to do that is I've actually rewritten some of the factors here, and let me move that into place. And if we were to actually exercise these products, we would end up with these these two terms, right? We would end up with this term and this term, right? This guy here is multiplying this by that, and this guy here is multiplying this by that. And what I want you to notice is if I were to switch E and B, right? Well, first of all, B and E are dummy indices, right? That's really the best way to see this. B and E are dummy indices, and therefore I can rename them. So one way I can rename them is I can call B E and E B, right? If I wanted to. Now, it just so happens, though, that if I were to swap E and B, right, then this sum with E and E is now summing over partial VE, partial I. Here the sum was partial VE over partial I, but E was in the other slot. That first slot was VB over partial J, right? But the second sum here is VE over J and VB over I, which is the same thing since you're summing over all of E, right? So this sum of these two is the same as this sum over these two. In other words, this whole thing actually symmetrizes on B and E, right? That's the point I'm trying to make here. That when you execute this product with B and E in place, you get the exact same thing as if you swapped E and B. And the reason that's important is it's not totally evident normally the way we normally do it. Like normally I would say, if I had any two indices over C and D, I would immediately say it's symmetric because VC and VD are the same things. But that's not the case here. VE theta I and VB theta J, those are different objects because the denominators are different, right? If this was an I and they were both by I, then they would in fact be the same and it would be symmetric here too. But it isn't. But then again, they multiply but they add this other term in. So this sort of extends the sum to make it symmetric over I and J. And because of that, you actually have a symmetry here, a functional symmetrization between B and E. And because of that, we are going to blow this up into two parts with B and E and B swapped. And let's do that. And so here it is, right? What I've done is instead of minus 2/3 B, C, D, E, I have minus 1/3 B, C, D, E, and then minus 1/3 E, C, D, B, right? But this and this are the same. So when you add them up, you get minus 2/3 B, C, D, E because of the way of the context it's in. This context made it symmetric. Okay, so now that we know that we can work with this guy, and don't make the mistake of thinking this thing is universally symmetric in E and B. It's not. It's only because we know that we're multiplying by this thing that we can actually do this little maneuver. You know, another way to look at it is that I'm symmetrizing over B and C, right? I've got somehow B, C, D, E, and I want a notation to say, and additionally symmetrize over B and C, which would be, if I was to somehow create a new notation, maybe this under slash, or this under bracket, showing that B and E is also symmetric, well, what would that be? Well, that would be 1/2 B, C, D, E plus E, C, D, B, right? That would be the definition of my underbar on B and C, right? And so what I've really done is that this is now appearing up here, right? Or I'm substituting, actually what I'm doing is I'm taking this and I'm substituting it for this, because that is going to be sort of equal to its symmetric part in this context. All right, so now we can start working from this position. All right, so now we're going to apply the definition of the Christoffel symbols of the first kind. I've kind of worked it out in advance here. But, understanding, of course, that our notation, I like this because it shows all the three different kinds of notations, right? The full partial derivative form, the comma form, and the semi-partial form. Ironically, of course, we don't use any of those. We use a straight line there for the comma. But with that in mind, we're going to make this substitution right into here and here. And understanding that this, although it's got that symmetry, this is where you can really run afoul of this sort of symmetrization problem. But understanding the definition of this is simply this, right? Their non-standard definition of their anti-symmetrization is just this expression, right? we make this direct substitution for that term and for that term, and we get these terms. And then we make the substitution for this, where this additional 1/2 comes in. So I make that a 1/6, and then we blow this all up, right? So this term right here is this. This term right here is this. You'll notice E is this thing is a partial derivative with respect to E. But this Christoffel symbol of the first kind is all based on first partial derivatives of the metric. So the metric ends up with two partial derivatives, right? So the derivative of a Christoffel symbol is going to be a second derivative in the metric. And here you'll see that for all these three terms, the last derivative is with respect to the superscript E, right? Or the subscript E in this case. So, and you expect to see that trend for all of them. So this Christoffel symbol derivative is this line, and D is the last derivative taken, right? D is the last derivative taken. And we're applying this definition. So we do it all, and I've colored these boxes to show the ones that are actually the same, right? The partial derivative of G, B, C, D, E is the same as the partial derivative of G, B, C, E, D, because you're always symmetric in the items on the right and left of the slash. Not because you always are, but because the metric itself is symmetric in its two indices, and partial derivatives are symmetric because the order of partial differentiation doesn't matter. So this and this are the same, as well as that. So these three add up. Basically, this cancels with one, and you're left behind with one of those. And that's true for these green ones and these like sort of grayish ones and these red ones. The red ones, there's 4 of these guys, right? 4 of these guys get added up. But you'll notice that this is the same combination of indices as out here, right? So EBDC is the same as BECD, which is the same as BEDC, which is the same as EBCD, which is the same as EBDC. I guess this is literally the same, but these other 3, they're all the same too. So the one that actually seems to constructively add is also the one that's subtracted from this guy outside. So it'll be interesting to see how that plays out. So anyway, so now we can take these guys and add them up. All right, so when I do that, I get this, right? This is, I'll block it off, right? GEDC, that minus 1/6 times this. So there ends up, out of all these 3 times 6, 18 terms, we end up with 6 terms, right? And here's the one that adds up. This is the red one that adds up with 4. This minus 2 is these 2 blue ones end up being a minus 2, but the others are just sort of straight. Now, the thing about the others, though, is if you look at it, remember, this here, this whole thing, which is this, is directly to be substituted right here. So the symmetrization is still in effect. So we still are allowing ourselves an EB symmetry. So if I consider the EB symmetry, then ECDB should be the same as that. And there it is, ECDB. So those two actually can be combined with a factor of 2. And likewise, BDCE would be EDBC. This and this can be combined also. So I can combine them, and then everything will have a factor of some multiple of 2 in front of it. And so I can pull that out. So this is me combining this with this, and that's what that is. And then you combine this with this, and I think you get that one. Then this one here is this guy here, and this one here is this guy here, and I pulled out a factor of 2 to get a third, right? So that's how we go from these things to this. And I should include this guy, right? So so what we're now working on is that. And then if we do all of the subtractions, we'll end up with, this guy will come in as a negative 1/3, a negative 1/3. This will be 3/3 minus 2/3, so that's a positive 1/3. And then that's a minus times a minus, so that's a positive 1/3. So what do we finally end up with? let's see. Let me do it out. I'll put it right under this thing here. So now if you look at their answer is in terms of the Riemann tensor ECDB, right? So if we plug this idea into here, what do we end up with? So that would, if I literally took these and put it in here, I'm just doing this to sort of, I mean, we could keep working, but we need to land in notation-wise the same place they do. And there's a lot of symmetries here that we don't want to deal with. So we're just going to make sure we land in the right place. So EBDC, check, we've got it. CDBE is the other positive term, check. EDDB, there shouldn't be two Ds. Hold on. Yeah, this, it should be ED, but this should be, M corresponds with the third one, which would be, M corresponds to the last one, which is B, which is executed first, and K corresponds with the second index, which is C, right? So EDBC, and we have that EDBC in a negative, so that's good. And CBDE, I have BCDE, which is the same thing, just symmetry on the G. So check. So this guy here, these do what we want them to do. Now what about the factors? Do we have all those right? The Riemann tensor is 1/2 times this. So if I multiply by a half out in front of it all, then I would have to multiply by 2, and then I would end up with equaling 2/3 RECDB, just like that. Okay, good. So we got there. And notice this step here used the fact that we are in normal coordinates where the derivative of the metric is 0. And remember, this is all at the point P, right? So this is fine to get rid of this because it's all at the point P. And all of these second derivatives are understood to be evaluated at the point P. So we have discovered this fact right here. Again, just utilizing, we haven't utilized everything though, right? Like I said, we still haven't utilized, we've utilized the normalness, but not the Riemann normalness. The other day I said, by the way, that, the word normal coordinates and Riemann normal coordinates are not really the same. Usually, it is true that very frequently people say normal and they mean Riemann normal coordinates. I'm still going to point out probably in the next lesson why this doesn't really jive. I just want to emphasize that we can eliminate this just based on these facts, right? That this is 0 at the origin, right? We still haven't really fully utilized the nature of the geodesics, right? The geodesics being straight lines hasn't been fully exploited quite yet. Close, but not quite. And in the final proof that we did, we haven't really fully run down that total symmetry. But we're still in a good position. We've still got this 2/3 RECDB. So we're in great shape. So where does that leave us? So where does this leave us? We have calculated this. We walked through all of this. We get to the end. We're happy to replace that with 2/3 ECDB. So that goes away. So now we've introduced that because of our calculation, which puts us right here in a very solid position. Everything is a function of theta, right? So we should have a little theta here. I'll blow this up a bit. These two things are functions of theta because V alpha is always going to be a function of theta. This notation, remember, this notation is non-standard. One way we could get rid of that comma, and that might give a hint that it's non-standard notation. But regardless, we know what that means, right? We understand that this bracket does not literally mean the anti-commutator like it seems to say. And now we have this tensor in our coordinate system. Now, remember, we always lean on the fact that just because we calculated this in one unique coordinate system, because we recovered the tensor itself, it's true in any coordinate system, right? But we're going to persist in our normal coordinates. And so now we move into the next phase of the proof, right? The next phase of the proof then starts taking this thing. And remember, we ultimately need the determinant of this, and then we need to integrate the determinant of that. So we still have a bunch of ways to go. But before we do that, I need to go back and justify all of my complaints about this term, which I've been talking about a lot. You know, this whole thing being equal to 0, this whole thing being equal to 0. I keep saying that this whole thing could be equal to 0. So let's see why I say that is true next time and how that implicates the whole proof. Ultimately, right, if what I say is true, we end up essentially right all the way down here at the same spot, but we don't have that term. We just have this expression only. And so clearly we've got to get our Riemann tensor in there with just this guy, right? And so we'll talk about that in the, I guess, the next lesson.